Hello again, and welcome back. This lesson here is on finite differences and what those mean. Now, finite difference is a new word, but it's something you've been doing in math for sure since beginning of your time at El Capitan High School. Um, Now, what are finite differences? Finite differences are just the changes in the y value. All right, finite differences are the changes in the y value as x changes by 1, typically. It's also, in my eyes, known as just the rate of change. Now, we're going to use the finite differences, and I want you to get used to that terminology because that's what this book will use, but it's really just the rate of change. And what we're doing in this lesson is we're exploring the finite differences of certain polynomials to see if there's a pattern. And you might have noticed it before, but we're formalizing now because calculus is all about rate of change and how things are changing instantaneously over time, and looking at these finite differences of the rate of change is very important. So this first one here, I have f of x is equal to x squared. And I put a table here similar to what you'll see in the first problem of from -3 to 3 inputs, and then your outputs are 9, 4, 1, 0, symmetric, 1, 4, 9. All right. So finite differences are these change in y values that we would do right here. This is what they call the finite differences, as x is changing by 1, of course, which, again, I always also know it as just the rate of change per 1. Right? So from 9 to 4, we're looking for pattern. Let's just write down what the differences are first. How do you get from 9 to 4? You minus 5. From 4 to 1, you minus 3. From 1 to 0, we minus 1. 0 to 1, we add 1. 1 to 4, we add 3. 4 to 9, we add 5. All right, Mr. Heim, we found the finite differences, and you're telling us now look for a pattern here? Well, let's see. Is there a pattern amongst these finite differences, amongst this rate of change, how these y values are changing? Well, if you look carefully, from -5 to -3, that's plus 2. From -2 to -1, that's plus 2. From -1 to 1, that's plus 2. That's plus 2. That's plus 2. So what's that mean? If all of these are plus 2, that means that the finite differences here have a constant rate of change. And what has a constant rate of change are linear patterns, right? If something keeps going plus 2, plus 2, plus 2, plus 2, well, that's a linear pattern. So what that means here is that x squared, the rate of change of x squared, the finite differences, actually follows a linear pattern, right? The graph of these finite differences, so we'll call it x, and we'll call this the change in y's. If we were to graph this, it would be some sort of linear line with a rate of change or slope of 2. We don't necessarily know where it starts, but we know that it has a rate of change of 2, which is fascinating, by the way, in case you don't make a connection, because we just somehow think, don't know if this is true, have a connection between x to the squared and linear patterns, right? A connection between two different functions that we've always studied. So we're going to keep going. Let's look at some of these examples down here. Now, the instructions are similar to what you'll see. Describe, if any, the pattern of these finite differences. And I created two functions here, different than what you'll see, but just to help you hopefully get a sense of this. So I'm going to go from -2 to 2, because that's a very common set of numbers to check a graph at. Right. And I'm just going to do this in my head, because get stronger at mental math. If I plug in -2, -2 squared is 4, 4 times 3 is 12. 12 minus 4 would be 8, 8 plus 1 is 9. If I plug in -1, that would make that +1, which is just 3. That would make that -2, so 3 minus 2 is 1, 1 plus 1 is 2. Plug in 0, those would go to 0, you're just left with 1. Plug in 1, it would just be 3 plus 2 plus 1, which is 6. And plug in 2, you'd be at 4, 12, plus 4 is 16, plus 1, you'd be at 17. Right, so those are the outputs for that function. Now we want to analyze the finite differences, the change in y values here. So from 9 to 2, it's minus 7. From 2 to 1, it's minus 1. From 1 to 6, it's plus 5. From 6 to 17, that's plus 11. Now, is there a pattern amongst these numbers here? Is this a pattern? Well, let's see. From negative 7 to 1, that's plus 6. From negative 1 to 5, that's plus 6. From 5 to 11, that's plus 6. So these finite differences here also they also have a constant rate of change, which means that it's following a linear pattern. With, if I go into more detail, a rate of change equal to 6. Okay. So that's interesting too, because we just did another quadratic, and the finite differences were also linear. Maybe you see something, maybe you don't. Let's look at the next one, Hein of x, because and I couldn't come up with anything, and yeah, maybe I shouldn't go with Hein. It's a little cocky and full of myself. Let's go with I don't know, pen of x, because I see a pen in front of me. Why not? Pen of x is equal to negative x squared plus 2. And I'm going to look at my function from negative 2 to 2 again. Right? At negative 2, you'd be at 4. Make that negative 4 plus 2 would be negative 2. At negative 1, it'd be positive 1, negative 1, and then negative 1 plus 2 is positive 1. 0, you'd be at 2. At 1, you'd be at 1, negative 1 plus 2 is 1. And at 2, you'd actually, I think, just be symmetric here, and you'd be at negative 2. Now let's look at these finite differences here. So from negative 2 to 1, that's minus or plus 3. From 1 to 2, that's just plus 1. From 2 to 1, that's minus 1. And from 1 to negative 2, that's minus 3. Do these finite differences have a pattern? And the answer is yes, they have a pattern where their rate of change is negative 2. So just like previously, these finite differences follow a linear pattern with a rate of change of negative 2. So like it would be some sort of equation, y equals negative 2x plus c for some integer c. Now that's, again, calculus knowledge, that or like beyond math. C can be any number. This right here is an element of, it's an e, and that notation is how you say the integers without having to write integers every time. Even up here, this rate of change would be 6x plus some element c, where c is an integer. And this you don't need to know. Again, this is beyond the scope of this class, but if I want to think about majoring in math, that's kind of like, the way you write. And then up here, we know that it would be some sort of y equals 2x plus some value c, which we don't know yet. It's not necessarily a way to know where c is an element of the integers. So what's interesting here is we just did 3 examples, and that's by no means a way to prove that it works for every time, but at least gives us more confidence that when we have a quadratic equation, which means to the second power, when we have a polynomial to the second power, the finite differences, the rate of change, always followed a linear pattern. Right? Now, going one step farther, what type of linear pattern did it get? Or could we have predicted the type of linear pattern, the rate of change of that linear pattern from just a function? Now, I'm not going to give this away. I'm going to see if anyone can figure this one out, but I'll say some stuff that might help you. This function was f of x equals x squared, and the finite differences rate of change was 2. This function down here, g of x, its finite differences, its rate of change, it had a rate of change of 6. And this function, pen of x, its finite differences had a rate of change of -2. Now there is a way to do it, and hopefully you see the pattern. How can we have gotten 2 from just that function, f of x equals x squared? How could we have gotten 6 from just that function, g of x here? How could we have gotten -2 from just this function here? And there is a pattern to see. And once you think you see the pattern, that pattern actually holds true for all polynomials of degree 2. So any polynomial a n to the second plus anything that follows it, sorry you don't see that, so any polynomial that has a second power, if you figured it out up here, that actually holds true. And what you'd want to, I mean, this is more extra, this is, I don't even know if I assigned this extra credit or not, but the idea that you'd want to explore is, does it hold true for polynomials of different degree? So if you looked at polynomials that were linear, does it hold true? If you looked at polynomials that were constant, which to the 0 power is really just, y equals some value a, does that hold true? If you went higher, if you looked at something to the 3rd power, does that hold true? And that would be something for you to explore and see if your pattern holds true, because there is a pattern here, and hopefully you see it. So that's finite differences, and really neat because, again, in summary, just these examples, we made a connection between quadratics and linears, 2 functions that maybe you didn't know were actually connected to each other. Good luck on the assignment. Please come to office hours if you need any help.